In section 6.2, we talked about the standard normal distribution. That's a normal distribution where the mean is 0 and the standard deviation is 1. However, the data in most normal distributions doesn't have a mean of 0. That would be kind of rare, unlikely. So we need to talk about how to find probabilities when we have a non-standard normal distribution. And one thing that would allow us to do that is if we standardize the values like we do when we're comparing, say, ACT scores and SAT scores, which had different means. You may remember a while back we did a problem like that, and to standardize the scores so that we could compare them, we use z-scores. We could do that same thing in 6.3, but we actually don't have to because the calculator will do that conversion for us. In 6.2, when we wanted to find the probability that a value lies between some left boundary and right boundary that we were given, we used normal CDF and we just entered the left boundary and the right boundary. When we have a non-standard normal distribution, though, we also need to tell the calculator the mean and the standard deviation of our population. So we end up with 4 arguments inside that parentheses instead of just 2. For example, a water taxi sank in Baltimore's Inner Harbor. Among the 25 people on board, 5 died and 16 were injured. An investigation revealed that the safe load for a water taxi was 3,500 pounds. Assuming a mean passenger weight of 140 pounds, if you divide 3,500 by 140, you would say, well, the boat can carry 25 passengers. However, this assumption was made 44 years ago when people were not as heavy as they are today. So the NTSB suggests the old estimated mean of 140 pounds should be updated to 174 pounds. So now we should only be letting 20 passengers on the boat. Assume also that the weights of the passengers are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. If one passenger is randomly selected, what is the probability that he weighs less than 174 pounds? Just like we did in 6.2, the first thing we need to do on all of these problems is draw the standard normal distribution. That helps us determine exactly what we need to enter on the calculator. Here we have a normal distribution with the mean of 172 pounds and a standard deviation of 29 pounds. We want the probability that a randomly selected passenger weighs less than 174 pounds. 174 pounds is just a little to the right of the mean. And if we wanted to shade the side that's represented by less than 174 pounds, we would shade to the left. When I use normal CDF to find this probability or this area, I have to enter both a left boundary and a right boundary. In 6.2, whenever we shaded forever to the left, we use negative 9,999 as our left boundary because there aren't going to be any values out 10,000 standard deviations below the mean. So I'm going to pull up normal CDF, enter the negative 9,999 to my right boundary as 174. And if I close the parentheses right there, the calculator would assume that the mean weight of an individual was 0 and the standard deviation is 1, which is not the case at all. So I need to tell the calculator the mean weight of this population is 172 with a standard deviation of 29. Rounded to 4 decimal places, I would get 0.5275. And that's the probability that a randomly selected male would weigh less than 174 pounds if the population mean was 172 pounds. That really makes sense if you think about it. If I said, what's the probability that an individual weighs less than 172 pounds or less than the mean? If this is a normally distributed population, then half of the population weighs less than this mean and half weighs more than the mean. 174 is not very far from 172. So this probability that we got is not very far from 50% of the population. It's about 53% of the population would weigh less than 174 pounds. The other thing that we did in section 6.2, in addition to finding probability or area or percent, we were sometimes given one of those things and asked to find a z-score. In this case, it's going to be an x value because we're not talking about the standard normal distribution. But when we were looking for z-scores in section 6.2, we used inverse norm. And remember, the most important thing in using inverse norm is to remember that you have to enter the area to the left of the desired score, the x value that you're looking for. You have to enter the area to the left. So if I'm given the area to the right, I'm going to have to find its complement and use that when I'm entering these numbers into inverse norm. Now, in 6.2, since we were dealing with the standard normal distribution, we used inverse norm and only entered one value. We closed the parentheses right here. But if we're not dealing with a standard normal distribution, we do have to enter the mean and the standard deviation. Use the data from the previous example to determine what weight separates the lightest 99.5% from the heaviest 0.5%. All right, draw your normal distribution where your mean is 172 and your standard deviation is 29. And we're looking for a weight here. We're not looking for a probability, an area, or a percent. That's what tells me to use inverse norm. I'm looking for a weight that separates the lightest 99.5% from the heaviest 0.5%. Where would the heaviest 0.5% be? Less than the mean or above the mean? The heaviest 0.5% would be above the mean. There's some weight that I'm looking for such that only 0.005 is the area to the right of it, and 0.995 is the area to the left. These are the weights of the lightest 99.5% of the population. These are the weights of the heaviest 0.5% of the population, and I'm looking for this weight that separates them. So I use inverse norm. I always have to enter the area to the left, 0.995, and then also enter the mean and the standard deviation. I typed that in wrong. Let me try it again. The area to the left is 0.995. The mean is 172. The standard deviation is 29. And I got that weight, if we round it to the nearest, just round it to the nearest whole pound, it would be 247 pounds. So what that means is if we used 247 pounds for this cutoff, then 99.5% of the population would weigh less than that, and only 0.5% of the population would weigh more than that. And those are the only two things that we do in this section. We either are given a left and right boundary, and we're looking for the probability or area or percent of values between those boundaries, or we're given some probability and we're looking for the x value associated with that probability. So let's do two more examples. Both of these have to do with lengths of pregnancies. And the lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. I can draw that normal distribution. A mean of 268 days and a standard deviation of 15 days. And the A part says one classic use of the normal distribution is inspired by a letter to Dear Abby, in which a wife claimed to have given birth 308 days after a brief visit from her husband who was serving in the Navy. Now, that's almost 40 days, or that is 40 days longer than the average pregnancy. So, what we're trying to find out is what's the probability that she actually got pregnant when her husband was home from the Navy and had a pregnancy that lasted 308 days or longer. Well, 308 days is definitely to the right of the mean, and we're looking for the probability that a pregnancy lasts that or longer, which tells us to shade to the right. And whenever we've shaded to the right, we've used positive 9,999 as our right boundary. Since I'm looking for a probability, I use normal CDF, not inverse norm. And I have to enter the left boundary, which is 308, the right boundary, which is 9,999, the mean, and the standard deviation. Rounded to 4 decimal places, I got that to be 0.0038. In other words, this is less than 1%. There's less than a 1% chance that if the mean length of a pregnancy is 268 days, there's a less than a 1% chance that a woman would actually have a pregnancy lasting longer than 308 days. I will leave you to make your own conclusion about the next question. What do the results suggest? One other application of that same information about lengths of pregnancies, the mean is still 268 days and the standard deviation is 15 days. But this has to do with the classification of premature babies. If we stipulate that a baby is premature if the length of pregnancy is in the lowest 4%, find the length that separates premature babies from those who are not premature. Now, it's the fact that this says find the length, doesn't say find the probability or find the area or find the percent. So I'm not using normal CDF. The length is an X value. I'm looking for an X value that separates the shortest 4% of pregnancies from the longest 96% of pregnancies. If this is going to be a length of pregnancy in the lowest 4%, is that going to be to the left of the mean or to the right of the mean? The lowest 4% would be to the left of the mean, and we're looking for this X value, which only has 4% of the area, or 0.04, to the left of it. When I'm looking for an X value rather than a probability percent or area, I use inverse norm. I have to enter the area to the left of the score that I'm looking for. And then because we're not dealing with a standard normal distribution, I also have to enter the mean and the standard deviation. Rounded to the nearest whole day, I got that to be about 242 days. And that means that since hospital administrators have to plan extra money that it takes to care for a premature baby, there needs to be this definition of what we will consider premature and what's considered full term. We could use 242 days as our cutoff between premature babies and full term pregnancies, and that way only 4% of the babies would actually be what we consider to be premature. All right, the only two things in this section, finding probability area or percent using normal CDF, and then finding X values using inverse norm. Your homework is assignment 11, and you're ready to tackle it. Have a good day.